Hello everyone, welcome to another lecture of this series on fundamentals of structural analysis. So today we'll see another example to draw the shear force diagram and bending moment diagram of a beam. Okay, so in this case we'll be taking a different type of loading condition. We'll see how the relation is developing. So last time we have seen that the moment and the shear force diagram that we have got, the shear force diagram, the you can say equation, or you can say the expression that we have got, it was you can say defining a linear equation, and then for the moment we got a quadratic equation, and it was basically telling us that the moment diagram will be a parabolic of parabolic shape. Okay, so today we'll see with different loading condition, okay, with another loading condition, whether we are getting similar kind of relation, or similar kind of expression, or a different type of expression. Okay, so we'll try to understand that. So let's get started. So for today's I can say lecture, I will take a similar simply supported beam with point load. Okay, so let us take a simply supported beam supported with a fully pinned support here and roller support here, right? So this is telling this is a simply supported beam and without any axial load, because that's why I've given a roller support here, so there will be no axial load developed. And this is my point A, this is my point B, right? And suppose we have a load here. Okay, we have a, let me draw it with a different color. We have a load here which is of 30 kilonewton. Okay, and if I just draw the location of this particular load, so it is 1 meter from this end, and this is again the additional 2 meter, so that means the total beam length is 3 meter here. Okay, total beam length is 3 meter here. Fine. So now what we need to do, we need to you can say find out the bending moment and you can say shear force diagram. Correct. So first of all what we can do, we can draw the, you can say uh, we can draw the Peabody diagram for this. So here we will get a reaction, so this will be AY. The similar, you can say sign convention we are following throughout the lecture series. So AX, and we know it is going to be 0 again. Then we have 30 kilonewton load, and then we have here by reaction. Correct. So the distance of this is 1 meter, this is 1 meter, and this is 2 meter. I am not drawing it, we know it already. Correct. So from here what are the things we can find out, so we can say, if we know summation of fx equal to 0, right? So this implies that ax equal to 0, so we already knew it, right? Then summation of fy equal to 0 implies ay plus by is equal to minus 30. Correct. Or you can write it like this. Sorry, I think I did it wrong. Plus 30 would be a ay plus by minus 30 equal to 0, right? So in this case, ay plus by equal to 30. Correct. So this is one equation, and name it equation 1. Okay, now if I take moment about any of these points, let us say moment about A, so we can find out one of the reactions. So if I just draw it, write it here, so suppose summation of moment about A equal to 0. Okay, so what does it imply? If you see here, see this at this particular point, this 330 kilonewton load, which is at 1 meter distance, will create a clockwise moment and it will be positive, right? So I can say that 30 into 1 will be positive, minus this by here will create a clockwise anti-clockwise moment, which will be negative. So by multiplied by 3 equal to 0. Okay, fine. So then we can say that minus by is equal to minus 30. So minus 3by is equal to minus 30. So 3by is equal to 30. Correct. So from here we can say that then by is equal to 30 by 3, so 10 kilonewton. By is equal to 10 kilonewton. So if I use suppose this is my second, so from 1 and 2 we can say that in this case ay is equal to 30 minus 10, so 20 kilonewton. Correct. So if you see here what we got, this ay is equal to 20 kilonewton, this by is equal to 10 kilonewton, 20 plus 10 30 kilonewton, and we have the total load 30 kilonewton. So it is in equilibrium. Correct. We got the reactions from the equilibrium equation. Now as we want shear force and bending moment diagram, so basically we need to find out the internal forces, that is the shear force and bending moment at any point, so that we can develop a you can say expression out of it, right, for bending moment at any point of this along the length of this particular beam. So now in this case, as we have a point load, we basically have to cut two sections. One, you can say left hand side of this particular point load, another one right hand side of this particular point load. So suppose we have drawn one section here. This is my let us say this is my x. Okay, this is my x, and then we need to draw another section. We need to draw you can say another section the other side. So it will be somewhere, suppose here, and this is also x. Okay, this is also x, but the difference is here, for this case this x is the value of x when if we define this value x, it will be between 0 to 1. Okay, and this x will be between 1 to this x will be between 1 to you can say 3 meter, 1 to 3 meter, right? So I don't know how to define it actually. Okay, let it be. Maybe we can say x1 and x2, but in this case it won't help. Okay, let it be. So two sections will be making, first at this particular point, another for this particular point. So now what I will do, maybe I don't know whether this diagram is not, maybe this diagram is not correct, because another x will be something like this. It will be from 1 to this you can say 3 meter. Okay, now let it be. Diagram was correct only. Fine, let it be. So two sections we need to draw, right? So for first case, if we say that, suppose summation of fy equal to 0. Okay, summation of fy equal to 0, first section. So okay, let me draw the you can say free body diagram of this particular thing. Actually, I have done a mistake here. What is the mistake? I shouldn't have drawn here actually. I shouldn't have drawn here. I should have drawn the diagram here. The first section I will take somewhere here. So this is x, and this x will vary from 0 to 1. Okay, so for 0 less than or equal to, I mean greater than or equal to x, greater than or equal to 1. So x, the value of x will be from 0 to 1. So if we draw the free body diagram, so how it will be? This is the, you can say, the beam. Okay, and this length is x. Here we are getting ay. I will not draw the ax because already we know ax equals 0. Now as we are drawing a section here, so there will be some shear force. So suppose this is Vx, and there will be a moment, and suppose this is Mx. We are considering this point as x now. Okay, we are considering this point as x now. So you already know Ax equal to 0, so I am not writing it here. So from here, if we want to find out, so you can say, if I say summation of Fy equal to 0, so in this case, Ay, this Vx downwards, so minus Vx is equal to 0, right? The value of Ay we know 20 kilonewton, we have written already. So 20 minus Vx equal to 0. So from here we can say Vx equal to 20 kilonewton. Directly we got. Now for the same section, if we say summation of Mx equal to 0, so what does it imply? So at this particular point, there is a moment mx, so minus mx because it is anti-clockwise, so minus mx. Then there will be a clockwise movement developed by this ay plus ay into x equal to 0. X is this distance, right? The distance is x, so the load force multiplied by lever arm, so this is the movement which will be developed clockwise, so that is plus equal to 0, right? So we can say ay is 20x, so what we can say, mx equal to ayx this side, right? So we can say mx equal to 20x. So what you can understand, that here the shear force is constant. The shear force that we are getting, it is a constant. It is not changing at any section, right? And in the other case, what we are saying, for the moment, it is one order higher. Okay, we have x with first order, so one order higher. It is a linear equation with one order higher. Linear equation with one order, right? It is not a constant, it is a linear equation with one order higher, correct? So this is the pattern we are getting for the, you can say, the beam with a point load. Okay, so let us see for the other section. Now what we will do, we will take the other section somewhere here. Now we have this x, and this x will vary from 1 to 3. This x will vary from, now this x will vary from 1 to 3, because 1 meter already you have got this, right? So for this will be varying from 1 to 3. So I would say that for 1 greater than or equal to x greater than or equal to 3, for 1 to 3. So now if we can draw the, you can say, diagram, it will be something like this. Here I have 30 kilonewton load. This is my AY. Okay, this distance is 1 meter, correct? And here I have a Vx. No, sorry. Yeah, here I have a Vx, and I have a moment here Mx. I draw from the left side only. I draw from the left side only. So from here, if I try to find out the shear force and bending moment, or from this, so I would say summation of Fy equal to 0, which implies Ay minus 30, this one, the load, minus Vx equal to 0. Okay, so in this case, Vx equal to 30 minus, is it correct? No, Vx equal to, how much we are getting? 30 minus 30 will do plus, so it will be, so we'll get Ay minus 30, because here minus is there, so again it will be multiplied with minus, so we'll get Ay minus 30. Okay, and here Ay we know it is 20 kilonewtons, so we can say Vx equal to 20 minus 30. So ultimately we are getting Vx equal to minus 10 kilonewton. So again you are seeing this is the shear force that we are getting, it is constant. But now it has changed its sign. Why it has changed its sign? So that means on the right hand side of the point load, okay, from this particular point load on the right hand side, everything will be in the negative side, because as there is a sudden load applied, so first the shear force will develop from here, it will be constant, and there is a suddenly one point load applied, so it will change its direction, then again it will go constant. Okay, so that's why you can see here the values are constant, but here the direction has been changed for the Vx, correct? So now similarly, if you can try to find out the moment, so summation of mx equal to 0, which implies, so we can say minus mx, then again minus this one. So this one, how much? This length, you can see this is 1, and this is 1, and rest we have 2, so 2 minus x, I think, right? Yeah, so 30 multiplied by 2 minus x. Am I writing it correct? 2 minus x, no, sorry, not 2 minus x, it will be this whole one is x, this whole length is x, so x minus 1, 30 multiplied by x minus 1. Okay, because again it will create a you can say a moment which is anti-clockwise, right? And then I think draw this one, what we have drawn earlier, it was correct only. Here also it will be this x, actually this is also x. Okay, the second case actually, x from 1 to 3 if we take. So in this case, if you see the equation that we are getting, minus mx minus 30 into x minus 1 minus or plus, sorry, plus here ay, which will create a clockwise moment, so ay into x, so ay into x equal to 0. Now we know ay is 20, right? So we can say here what we will get, minus mx minus 30x minus 30 plus ay is 20x equal to 0. So here we got 10x, so we can say minus mx equal to plus, you can say 30x plus 30, no sorry, I made a mistake, it will be plus 10x, okay, plus 10x plus 30, okay, plus 10x plus 30. Did I make any mistake? This 30 minus 30x minus plus 30. Yes, here I made a mistake. I was also thinking. So now if I say mx equal to 30 minus 10x, so this is the equation. So here also you can see this is a linear equation. This is a linear equation, but one order higher, right? One order higher. So from here what you understand that both the cases the moment is linear, I mean giving us linear equations, so it will not be a parabolic shape, it will be a linear line, right? Line shape with some increment or decrement that we will see. So and the shear force that we are getting, it is constant. The shear force that we are getting, it is constant. So now let me make an Excel sheet just to I can say create the bending moment and shear force. So we have you can say the beam starting from 0, and what I will do, I will take every, you can say 0.25 interval, so plus 0.25, right? We have a beam of 3 meter. I'll just take this. We have a beam of 3 meter, correct? So from 0, in case of shear force, if you see from 0 to 1 meter, the equation, I mean the value that we are getting, it is Vx equal to 20. So it will be something like this. We know how it will be, but I'm just putting it here so that we can easily generate. So from 0 to 1 it is 20, and then from here it is minus 10, correct? From here it is minus 10. So if you see how will be the shear force diagram, so you can draw it easily and just show you. If I go to insert recommended charts, okay, area, fine. So you can see here the shear force diagram is coming something like this. So here, as we have taken, I mean 0.2 difference, so in this case it is giving a slope basically. Otherwise how it will be, generally when we'll be drawing it, it will be something like this. If you see, this is my beam, here I have the supports, and here I have 30 kilonewton load, right? So I will have a line like this, okay. This is my beam, fine. So here I have 20 kilonewton. It is going constant up to here, right? So constant up to here, then it is changing the direction, and it is going constant again up to this, and it is my minus 10 kilonewton. Okay, but as here in Excel, as we have given 0.25 difference, I mean one point is here, another point is here, correct? So that's why we are getting a slope like this, but actually there will be no slope. It will be like this. It will be like this. Okay, so this is my shear force diagram. Here at this particular point, the total shear force is 30 kilonewton only. The total shear force, if you see, it is 30 kilonewton only. 20 here, 20 here, 10 here. So total shear force is equal to my this load only. Just it has changed the direction. If I did not assign any you can say sign here, as I have already shown the direction. So the total, if you see here, the total is here. This total is 30 kilonewton, as we have a direct point load here, 30 kilonewton. Correct? Okay. Now, if we draw the bending moment diagram, again I'll go here, and for bending moment diagram, again I will take this, I'll paste it here, and again for bending moment diagram, what is the formula? For up to 1 meter it is 20x. Okay, up to 1 meter it is 20x. So I will make it equal to 20 multiplied by x, right? So this is up to 1 meter, and after 1 meter, what is the formula we got? It is 30 minus 10x. So it will be equal to 30 minus 10x. Fine. Okay, so I'll take this, I'll go to insert recommended charts area. You can see this is the bending moment diagram that we are getting and that we are expecting. So this is what how we will get. Why? Because if you see here the bending moment diagram, we can also solve it now here. How it will be? So if you see, suppose for up to 1 meter, if I put x equal to 0, if I put x equal to 0 in this 20x, so how much it will be? X equal to 0 means 0. So mx equal to 0, 0. If I put here at 1 meter, that x equal to 1, so how much is the moment? So I am getting moment here 20 kilonewton meter. Okay, then if I put x equal to 1 here, then also if you see 30 minus 10x, x is equal to 1 means 30 minus 10, 20 kilonewton. So both the expressions are giving me similar value. That means these are in line with each other, right? And now you can change any value. If x equal to suppose 0.5, x equal to 0.5, how much it will be? 10 kilonewton it will be. So somewhere here. Okay, somewhere here, like that. So if you put like this, so you will see that you are getting a linear, as it is a linear equation, you're getting a inclined line like this, okay, which will end up here at 20 kilonewton meter. Now in the other side, if you put x equal to 3, you can see 30 minus 10 into 3, 30, so it will be 0, which we expect because it's a simply supported beam. Now we can put any value, suppose x equal to you can say 2 meter, so it will be 30 minus 10 into 2, 20. So if it is 2 meter, so this is totally 1 meter, then 1 meter moved. So somewhere here, so we'll get here as you can say 10 kilonewton meter. Okay, like that. If you put, it will be again a linear line, I mean inclined line like this. So now at any point you can find out and you can draw this diagram actually. So that's what we have done in the Excel. Okay, because it is easy. So if I see x equal to 2, here you can get bending moment as 10 kilonewton meter. Even from our manual calculation also we are getting this. Correct? But as I said earlier, that when we work in the real life, the bending moment diagram shall be drawn like this. On tension phase, we consider this as positive. Okay, this side, I mean the sagging as positive, right? We have already seen this. That's why will be downwards, it will be, we'll consider it as positive. If it is going up, then we will consider it as negative. So in our case, actually this will be my bending moment diagram, and for this we will be providing the reinforcement in case of RCC beams. This is 0. This is, okay, so this is my tension phase BMD. Okay, and this is compression phase BMD. This is compression phase BMD. Though we'll be providing reinforcement for this, you can say this moment at the bottom only, because we know this is positive, so this is a sagging moment only. But it is a bit confusing. So I think it is better to draw bending moments on tension phase like that. Okay, clear? So you can see, and now in this case what we understood, that with the change of loading pattern, okay, with the change of loading pattern, the expression for drawing the SFD BMD also changes. That means the pattern of SFD BMD also changes. Okay, so we will do many such you can say examples in our further lectures also, and we'll try to understand more about this particular thing, which is very much important actually to understand. Once we know what kind of you can say expression can be developed or can come due to the different kind of loading conditions, in this case then we can use our intuition to draw the bending moment or shear force diagram. We do not have to exactly find out the value, we just have to understand how it is bending, okay, how the moment will be developed. So then that we can do after understanding these particular things. So I hope it is helping you, or you are finding this series helpful for your developing your intuition towards SFD BMD. If you have any doubt, you can always write me in the comment box. I will try to solve it as soon. Thank you, and see you in the next lecture.